putting the limit comparison test into action. With our first example, we see that we have the series 2 to n plus 1 over the quantity n plus 1 squared. All right. Now, just thinking about this expression quickly, all right, we think, okay, if we were to FOIL out or multiply out our denominator, we have 2n plus 1 over n squared plus 2n plus 1. All right, so we can see that this expression right here is going to behave like 2 over n. All right, in essence, the n squared is the dominant term in the denominator, 2n is the dominant term in the numerator, 2n over n squared simplifies to 2 over n. So it makes sense to compare this series, using the limit comparison test, with the series 1 over n. All right? And maybe we can show that this series in fact diverges. Right? So what are we going to do? We're going to take the limit as n approaches infinity of our series, which is 2n plus 1. Let's try that again. There we go. Over n squared plus 2n plus 1 over the series that we know for a fact diverges, which is just 1 over n. And we want to find this limit, right? Now we've got fractions inside of fractions, so we know that we can just multiply by the reciprocal. So we multiply by n, so this is the same thing as the limit as n approaches infinity. When we multiply this by n, in essence, this n is heading all the way up there. So we end up having 2n squared plus n over, n squared plus 2n plus 1. Right? And that's a limit that we've been dealing with many, many times over the years. We can see that we have the quadratic happening in both the numerator and the denominator. So we're going to focus on the two coefficients, and the leading coefficients lead us to a limit of 2. All right? So that was the c from the previous video. All right? Our limit is equal to some value c being positive, in this case 2. What do we know? Well, since the series that we picked was divergent, that means that the series we're curious about also diverges. So this is a situation of a divergent series. With the second series, we have the 1 over the quantity 2 to the n minus 1. Now this series seems to be behaving a little bit like a geometric series, but it's not a geometric series because of that minus 1 in the denominator. Right? But we can compare it to a geometric series that we do know about. Specifically, the geometric series 1/2 to the nth power, which we know is the same thing as 1 to the nth over 2 to the nth, which since 1 to any power is 1, it's 1 over 2 to the n. So why don't we compare our series with the geometric series that we actually know converges? And we know this converges because r is less, the absolute value of r rather, is less than 1. Let's make our limit. So we have the limit as n approaches infinity. The series that we were given is 1 over 2 to the n minus 1. Our series is 1 over 2 to the n. And just like before, we're going to multiply by the reciprocal. So we have the limit as n approaches infinity. Our first series is 1 over 2 to the n minus 1. The reciprocal of our denominator is 2 to the n over 1. So we can see now by combining that we have the limit as n approaches infinity. And our numerator is 2 to the n, and our denominator is 2 to the n minus 1. Right. We've done exponential functions inside of limits as n approaches infinity before. All right. They are going to grow at the same rate. All right. So this is actually going to be equal to 1, but if you prefer, you can certainly divide each of the terms by 2 to the nth. All right, giving us what looks like 2 to the n over 2 to the n, and then this is 2 to the n over 2 to the n minus 1 over 2 to the n, which ends up being the limit as n approaches infinity of 1 over 1 minus, 1 over 2 to the n. As n approaches infinity, that term goes to 0, so we have 1 over 1 minus 0, or 1. Right, which you can get that from here. That's quick enough to do that. 1's our c. Right? So because the ratio of the two as n approaches infinity is equal to that value, we know that both series either converge or diverge. Since we know that this series that we were using, 1 over 2 to the n, is a convergent series, then that means that this series right here must converge as well. And last but not least, we have the series 3n plus 2 over n cubed minus n squared. So if we look at the dominant terms, we have 3n and n cubed. All right, so this is going to behave like the series, like the situation of 3 over n squared. Right? So why don't we use the n squared p series here, 1 over n squared. So I'm going to just do it over here since I have a little bit more room. We've got the limit as n approaches infinity. The series we're curious about is 3n plus 2 over n cubed minus 2n. The series we're going to use is 1 over n squared. That's our converging p series. And as we rewrite the limit, we can see the limit as n approaches infinity. We're going to multiply by the reciprocal, so we're going to multiply by n squared, and just like before, that n squared is going to head up into our numerator, so we have 3n cubed plus 2n squared in the numerator, and we have n cubed minus, that's a minus, 2n in the denominator. Right? Our leading coefficients are 3 and 1, so this limit will turn out to be 3. Since the series we used was a convergent series, then that means that this series converges as well. Okay. So we have the limit comparison test in action. Now, the idea with the limit comparison test is that you may not necessarily have to go through all the steps. All right, if it's a multiple choice question and using the limit comparison test, and let's say it's one of the, again, it's the Roman numeral question where you're given 3 series and you have to determine which, if any, actually converge. So let's say that you're given this is one of the 3 options. You don't have to go through all of the limit notation for a multiple choice question, right? But just have the general knowledge of the limit comparison test to say, oh, well, this is working like 1 over n squared. 1 over n squared is a convergent series, so this series in purple is going to converge as well.